Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Layer 3 of the OSI model, known as the network layer, is responsible for enabling communication between devices located on different networks. This layer introduces logical addressing and path selection, allowing data to move from a source to a destination across multiple segments and intermediary devices. Unlike the lower layers, which focus on local transmission and framing, Layer 3 is where routing begins, making it a central component of large-scale communication. Without Layer 3, data would be confined to local areas with no means of internet delivery. In network design, the network layer plays a critical role in segmenting and linking systems at scale. Routers, subnets, and IP addresses all operate here, providing the tools needed to move traffic between network zones, enforce separation, and support thousands or even millions of devices. The functions carried out at Layer 3 make modern networking possible, as they enable diverse environments to coexist, communicate, and scale efficiently. The reach and logic of Layer 3 are what allow enterprises, data centers, and the global internet to function cohesively. At its core, Layer 3 is responsible for managing the delivery of packets between devices that may reside on entirely different networks. It does this using logical addressing schemes and a series of forwarding decisions. While Layers 1 and 2 move signals and frames within a single broadcast domain, Layer 3 takes charge when data must travel between separate domains. It determines the best path for each packet, directs it accordingly, and ensures that it reaches its intended destination through the proper routing logic. The most important feature introduced at Layer 3 is logical addressing, particularly in the form of IP addresses. These differ from MAC addresses, which are hardware-specific and static. IP addresses are software-assigned, flexible, and structured hierarchically. Layer 3 supports both IPv4 and IPv6, each with its own format and rules. These addresses are globally unique within their context and can be reassigned, routed, and grouped into networks and subnets, which adds a layer of control that is essential for wide-scale communication. Each packet at Layer 3 contains a header that carries vital information for routing and delivery. The packet encapsulates the transport layer segment and includes source and destination IP addresses to guide its journey. Other fields in the header may include a time-to-live value, which limits how long a packet can circulate, and a protocol identifier, which tells the receiving device how to process the payload. These headers are read by routers and form the basis for every decision about how to forward data. Routers are the key devices operating at the network layer. Their main job is to evaluate incoming packets, consult routing tables, and decide on the most appropriate next hop to send the data closer to its final destination. Routers make these decisions based on destination IP addresses, and their logic is influenced by configuration, routing protocols, and metrics such as hop count or link cost. By interpreting Layer 3 headers, routers can maintain separation between networks while enabling controlled communication between them. Routing and switching are often compared to highlight the distinction between Layer 2 and Layer 3 behaviors. Switching, which happens at Layer 2, involves using MAC addresses to forward frames within a local area. Routing, on the other hand, uses IP addresses to move packets between separate networks. Switching is fast and confined to a single broadcast domain, while routing requires more logic but enables broader connectivity. These differences are central to understanding how traffic segmentation and interconnecting operate. Layer 3 defines broadcast boundaries, meaning that routers do not forward broadcast traffic by default. Each network segment is limited in how far a broadcast can travel, which prevents excessive traffic from overwhelming the network. By placing routers at boundaries, network designers control the size of broadcast domains and help maintain performance and scalability. This behavior contrasts with switches, which forward broadcasts within the local network but cannot prevent their propagation. Packet fragmentation can occur at Layer 3 when a packet is too large to be transmitted over a link with a smaller maximum transmission unit, or MTU. The network layer splits the packet into smaller fragments that can traverse the link. Each fragment is sent independently and reassembled at the destination using identifiers in the packet header. While modern protocols attempt to avoid fragmentation, it still plays a role in network compatibility and is important to understand for troubleshooting and exam preparation. Assigning logical addresses is a foundational task in Layer 3 network design. This can be done manually through static assignment or dynamically using protocols like DHCP. Static assignments provide full control, while dynamic configurations are efficient for managing large groups of devices. Address assignment also connects directly to subnetting, where networks are divided into smaller segments for traffic control and organization. This layered approach to addressing creates both order and scalability within complex network environments. Routing protocols are introduced at Layer 3 to automate the selection of optimal paths through the network. These protocols use algorithms to compare routes, update tables, and adapt to network changes. Distance sector protocols, such as RIP, use hop count to evaluate paths, while link state protocols like OSPF build maps of the network topology to choose efficient routes. These concepts are explored in greater depth in later domains, but their roots lie in the fundamental logic of the network layer. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Subnets play a vital role at Layer 3 by dividing larger IP networks into smaller, more manageable sections. Subnetting allows network administrators to control traffic flow, reduce broadcast domains, and improve performance through logical segmentation. It also enhances security by isolating groups of devices and controlling access between them using routing policies. Subnets are defined using subnet masks or prefix lengths, and their implementation ensures efficient use of IP address space while supporting scalability in both small and large environments. Loopback interfaces and virtual addresses are also Layer 3 features that serve important functions in network operations. A loopback interface is a logical, always-up interface that doesn't depend on physical hardware. It is commonly used for diagnostic purposes, router identification, and internal communication between software processes. Because it remains operational even if other interfaces go down, it provides a stable reference point for configuration and routing decisions. These virtual addresses help maintain control and consistency in dynamic environments. Several protocols operate directly at Layer 3, beginning with the Internet Protocol itself. IP is responsible for defining logical addresses and enabling packet delivery across networks. Internet Control Message Protocol, or ICMP, is another critical Layer 3 protocol used for diagnostics and network communication health checks, such as ping and traceroute. Routing protocols like RIP, OSPF, and EIGRP also function at Layer 3, providing path discovery, table updates, and dynamic route selection capabilities. Each of these protocols plays a role in building a functional and responsive network. The time to live, or TTL field, in an IP packet is essential for controlling how far data can travel across a network. Each time a packet passes through a router, the TTL value is decreased by 1. When it reaches 0, the packet is discarded. This prevents routing loops from clogging the network and ensures that undeliverable packets do not circulate indefinitely. In IPv6, a similar field, called a hop limit, serves the same purpose. These controls are fundamental to maintaining network stability and health. When a router makes a forwarding decision, it consults its routing table to determine the best path for the packet. The router examines the destination IP address, compares it to entries in the table, and selects the most specific match. It then forwards the packet to the next hop, which is either the final destination or another router that is closer to it. This decision-making process happens for every packet that passes through the router and is essential for efficient delivery in multi-segment networks. While a router primarily uses the destination address for forwarding, the source address also plays a role in communication. The source IP is used in return traffic, logging, access control decisions, and troubleshooting processes. Importantly, the source address does not change as the packet traverses the network, ensuring the recipient knows where to send a response. Layer 3 does not modify the packet content except when fragmentation is needed. preserving the integrity of both source and destination data. Encapsulation at layer 3 involves taking a transport layer segment and wrapping it with a packet header that includes all necessary routing information. This encapsulated packet is then passed to layer 2, where it is further framed for local delivery. Logical addressing is introduced here, and routing decisions begin based on the destination IP. Encapsulation ensures that data retains structure and meaning as it moves between networks, allowing for orderly and predictable communication across diverse infrastructures. One of the most impactful roles of Layer 3 is in supporting network scalability. Without routing, large networks would collapse under the weight of excessive broadcast traffic and poor performance. Layer 3 provides the structure and intelligence needed to divide, route, and control traffic efficiently across thousands of nodes. It allows networks to grow in size without losing coherence, supports the separation of services, and enables global communication through hierarchical addressing and dynamic routing mechanisms. Layer 3 is where true internet-ing begins. It transforms isolated segments into a connected system capable of supporting everything from small office networks to global data centers. Through logical addressing, packet forwarding, and intelligent routing, Layer 3 empowers all higher layers to function across geographic and administrative boundaries. For anyone preparing for the Network Plus exam, a strong grasp of Layer 3 concepts is essential for understanding how data moves across the broader internet. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.